What exactly happens during a system call? This video is titled Anatomy of a System Call, and in it I'll walk through all the actions that occur whenever a system call is invoked. I'll look at the sbreak system call as an example. Sbreak is found in Unix and Linux systems, and we're talking about the xv6 operating system kernel, and that is a simplified version of Unix and Linux. Here are the functions and files that we'll be discussing in this video. Every user mode program that wants to make a system call will need to include this user.h file. And we have a number of assembly code functions in usys.s that are run in user mode. The definitions in syscall.h are used both by the user mode code and by the kernel code. So this file is shared between both user mode and kernel code. Once the trap occurs, we will be thrown into the code in the trampoline page. This is assembly language code. And the user.vet code will then invoke the user trap function. User trap function will determine that we've got a system call and invoke the function Syscall. Syscall will determine which system call we want, and it will, in our case, invoke sbreak to do the system call that we're going to be looking at. Sbreak will then invoke growproc, which will actually increase the size of the address space. And then when everything returns, Syscall will then end by going back to user trap ret, and user trap ret will then jump to user ret, the assembly language code, which will execute the sret instruction and bring us back into executing user mode code. So let's begin with user.h. Any user mode program that wants to invoke a system call needs to include this file, and it contains a number of function prototypes. So it contains one prototype for each of the 21 system calls, and in particular we see the prototype for sbreak here. Sbreak is passed a single argument, and that argument is the amount to grow the heap by. It can be positive or it can be negative if you want to shrink the heap. It can also be 0. It returns the previous size of the heap, so if you want to know how big the heap is, you can just invoke it with 0. In the Risc-V system, arguments are passed in registers A0, A1, and A2, and so on. So this function has 3 arguments. Ours only has 1, so only A0 would be used. If there's a return value, and all of the system calls have a return value, that would be placed in A0. This function also includes, this file, user.h, also includes a number of other definitions for helper functions like printf and string length and so on, but we won't talk about those here. So next let's ask which function gets invoked when a user mode program calls something like sbreak or fork or read or write or any other system calls. Well, the answer is a short assembly language program that runs in user mode is invoked. Those functions are also often called stub routines, and they're all collected and all found in this file usys.s. This is an assembly language file that contains a short stub routine for each of the 21 system calls. This file is actually automatically generated by a Perl script, usys.pl. But I've shown here what goes into that file. It begins with an include, which is syscall.h. And let me just stop here because syscall.h is pretty straightforward, and I can dispense with it quickly. Syscall.h associates a number with each of the system calls. This number is how the user mode code communicates with the kernel as to which system call is desired. In our case, sbreak is 12. Okay, and so we include those definitions here. And then for each one of the 21 system calls, we have these 5 lines in the file. I've only shown the code, the stub routine for sbreak, but it's repeated once for each of the other 20 system calls. And what does the stub function look like? Well, it's got a label and a return, so it's like any function. It's also got a global, which exports that label, so it's visible in the linking phase. But primarily it has these three instructions: load immediate, eCall, and ret. Load immediate will move into register A7 some value. In this case, we remember that the sbreak constant was 12. So this just moves 12 into A7. And then we execute the environment call or eCall instruction, which performs the system call. At the point which any of these global stub functions is called, we can expect the arguments to be in registers A0 through A5. We can accommodate up to 6 arguments to any system call. And those registers will be unchanged by this load immediate, and so they'll still be valid. And the kernel will fetch the values that it saved for those registers, and that's how it accesses the arguments. The kernel code will also place or overwrite the A0 register with whatever the return value should be. So after the kernel comes back, that is, after we resume executing in user mode, at this point, A0 will contain our result, and we don't touch it, we just do the return instruction. So in Risc-V, whenever a function is called, the return address is placed in register RA, return address, and then the return instruction just simply copies the value in RA to the program counter. The kernel will preserve all registers except for A0, and so we can be sure that at this point the value that was in RA here will still be there, and so this can return properly. Okay, so we're executing in user mode, and at some point an eCall instruction is executed, and that causes a trap. After that, we execute in kernel mode, and then finally we execute the sret instruction in kernel mode, and that returns us to user mode, and we resume execution directly after the eCall instruction, which is the return instruction in the stub routine. So let's look at that in a little bit more detail. Here is the process from the trap all the way down to the sret instruction. A trap will change the mode into kernel mode, disable interrupts, save the program counter, and jump to the user-vec function. User-vec is located in the trampoline page, and it will save the user registers, load the kernel registers, and change to the kernel's virtual address space, and finally it will jump to user trap. We'll look at user trap in more detail, but it will figure out that it's a system call and so on. But eventually user trap will call user trap ret, and that will then invoke user ret, which is assembly code, and that will finish the process and execute the sret instruction. In particular, we'll go back to the user's address space, restore the user's registers, and then the sret instruction itself will change the mode to user mode and restore the program counter to whatever was saved and re-enable interrupts. Here's a diagram I used in an earlier video showing the same thing in a little bit more detail, from the trap to the sret instruction. Again, you see the assembly code in the trampoline page at user-vec being invoked to save the state of the process. It jumps to the user trap function, which then does some stuff and eventually calls user trap ret, and that restores the state of the user process along with user ret, and ultimately executes the sret instruction. So what happens in user trap? Well, we have a big if statement that determines the cause of the trap. Is it an exception, or is a device requiring attention, or is it a timer interrupt, or is it a system call? If it's a system call, we enable interrupts and then invoke the Syscall function, and after that returns, it invokes the user trap ret to begin the process of going back to the user mode code. We also check the killed flag. There's a Boolean value that is set if somebody wants this process to die, and if it was set, then we invoke exit. I've also hinted at here that there could be some process switching going on. the moment we re-enable the interrupts, it's possible that a timer interrupt could occur or a device could require attention. So the scheduler could get involved. And I tried to indicate that over here to say that any time between the interrupts being enabled here and the interrupts being disabled at the beginning of user trap ret, it's possible that we could switch to another process. But eventually we'll come back and finish executing whatever code is involved with the system call. So now let's take a look at the user trap function in more detail. So I'm not going to go over everything here, but we basically have an if statement that looks at the status and control register called scause to determine whether it's a system call or something else. And so we have some other stuff down here in the if statement. But with Risc-V, the scause will have a value of 8 if it's a system call. So that's what happens here. We basically execute the system call function. First, we check the killed flag to see whether someone has set it, and if so, we invoke the exit function. Exit will never return, so if that happens, this process will stop right here. But assuming it continues going, we then look at the EPC field in the trap frame. When the trap occurred, the code in uservec will save all the registers, and the program counter will have gotten saved in the EPC field. The program counter will point to the eCall instruction itself, and we need to advance it past the eCall instruction, which is 4 bytes, to the next instruction. That's presumably the return instruction in the stub routine. The eCall instruction is 4 bytes, so we advance it to point to the next instruction. So when we return, we'll execute that return instruction. Here we turn interrupts on, and then we invoke Syscall. After Syscall returns, down here, we check the killed flag again, and perhaps exit right there. The which device would be set if there's a device interrupt, but we initialize it up here to 0, and it's not changed, so we will not execute this yield function here. And then continuing with this function, after the yield, we call user trap ret, and then that, which is shown right here, basically restores the state and ends up going back to the user ret function down here and returning to the user mode code. After the function user trap figures out that the cause of the trap was a system call, it will invoke the syscall function, which is located in the syscall.c file. And here's what happens. Remember, at the time of the trap, the code will save all of the registers of the user mode process. And the stub function has preloaded into register A7 a number. In the case of sbreak, it would be 12, a number which indicates which system call is required. So the first thing we do is we get a pointer to the proc structure, and then we chase it to the trap frame and look at the A7, the register A7 field, and retrieve that. Okay, then what we're going to do is we're going to use that as an index into an array. So let me take a look at what occurs earlier in this file. This is a collection of function prototypes, and here we see sbreak, all lowercase. This is the function we're going to be calling to get the work done. And then we have an array. This array is called syscalls, and it's a bunch of pointers to functions. And so for number 12, where is it here? It's right here. We have the value of a pointer to the function sys sbreak. Okay, and even though these aren't in quite the same order, all 21 system calls are represented with functions to execute the system call, and the array has all 12 entries for each one of those. So that's what's going on here in syscall. We look up the and get the pointer to the function, and then we invoke that function. Okay, it's passed nothing, and it's going to return a value. Okay, and that value will be stored in the trap frame in A0, overwriting whatever was in A0. Okay, so that's where we actually call the sbreak function. Before we do the call, we just check to make sure that the user mode code is providing a legal number. So we check to make sure it's greater than 0 and that it's an entry in the Syscall's array, and that pointer has been initialized to something and is not null. So if it's all okay, we invoke it. But if the user has provided a bad system call number, then we print a message. Normally the kernel wouldn't just directly print a message for this sort of thing, but it would just return an error code. So we do see the error code being returned. We're writing a -1 into A0, but we're also printing some information here so we can debug both the kernel and the user mode program. The process ID, the process's name, and the number that was actually provided. Okay, so in this file we have a couple of other functions. So I want to look at this first one. These functions are helper functions that will be used in functions like sysbreak that implement the actual system call. So we need a way to fetch the arguments. So arg_raw will be passed a number. That's the number of the argument you want, 0 through 5. So we're switching on 0 through 5 here. And all it does is it goes into the trap frame and returns the value of the user's register A0, A1, A2, 3, 4, or 5. And then it returns that value. That is used by this next function, argint. And argint is just going to call arg_raw, but it's also going to store that value. It's passed a pointer to an integer, and so it stores it in that integer variable. We have a couple of others. There's arg address. It's exactly the same code. So the only difference is that the variable that it's being stored into has a type uint64 as opposed to integer here. There's also one for arg string. Okay, so fetch the nth word size system call argument. Okay, so that's the number between 0 and 5 as a null terminated string. Copy it into buffer and at most max characters. So in addition to the number of the argument we want, we're passed a pointer to some buffer and its size, and it returns the string length if okay, and -1 if there's a problem. So here we are fetching the address here and putting in a local variable address, and then we have this function fetch string to do the work, and fetch string is right here. Fetch the null terminated string at address from the current process, and it returns the length of the string and a -1 for an error. So here we see that it's calling copy in string. We discussed that in a previous video when I discussed the virtual memory functions, helper functions. So basically it's going to use the current procedures page table, and here's the address in kernel memory, and here's the virtual address and the maximum number of characters to copy, and then it's going to copy that and return the string length. There's also another helper function called fetch address, and the idea is the argument to the system call will be an address, and we want to go into the virtual address space and fetch a 64-bit value from the virtual address space. So this is past the virtual address, and the value that's fetched will be stored, and it will be stored at the location pointed to by this pointer here. So to do this, we see that the copy in function is used. We're passed a page table to indicate which virtual address space it is. And here is IP. That's the place where we're supposed to store the 8 bytes, right? This thing will be 64 bits or 8 bytes. And here's the virtual address. And here is the number of bytes that we need to copy. And well, IP is a pointer to 64-bit value, so the size of that is 8 bytes, so this is 8 here. We see it expressed slightly differently here, so this is also 8 bytes. First, I want to say that if there's a problem, we just return -1, otherwise we return 0. Here we're checking to make sure that the address that the user mode program has provided is correct. And we see that we're checking to make sure that the address, well, it better be somewhere between 0 and the size of the address space, right, the top of the heap, the break point. So we're checking to make sure that it is less than the break address. Okay, and then we are adding, well, 8 bytes to that. And again, we are looking to see whether it is not too large. Okay, and if there's a problem with it, we return -1. Now you might say, why in the world would we perform this check? Because clearly, if this is true and then you add 8 to address, this is going to definitely be true. But here is the thing. What about wraparound? We're using unsigned integers. What if address is way up at the very top of the 64-bit values, and when you add 8 to it, it wraps around? So this one could be okay, while this one is not. But if this one is below the size of the virtual address space, which is limited to, substantially limited, then we won't have a wraparound here. So this is the kind of thing where you have security flaws in kernels. So you need to be really, really careful with all possible values that the user code could provide. And so this is an example why this second check is actually necessary. Now we're ready to look at the sbreak function that actually does the work. It's located in the file sysproc.c, along with a bunch of other functions for other system calls. Some are pretty simple, like here's the one for the get PID, and all it does is simply go to the proc structure and fetch the process ID and return that. Each of these functions is passed no arguments and returns a return value that will go into A0. Other functions are more complicated. Here we see the fork system call, and it's just calling this function fork, which is located elsewhere, to do all the work. Let's go down here to where we see so let's go down to where we see sysbreak, and we see that it will call the function growproc to do the work. But first, it has a single argument, which is number 0 in register A0. So local variable n is here. The call to argint is just going to fetch the value from register A0 and place it in the variable n. And we are then going to capture the previous size of this process. So we are just getting the size field and saving it here, and that's what we will be returning. And then we call growproc to do the work. Finally, let's look at the growproc function, which comes from the file proc.c. So this will be passed a number of bytes, and it will grow or shrink the user memory, returning -1 if there's a problem. We check the number of bytes to see if it's positive, in which case we call uvm-alloc, or if it's negative, we call uvm-dealloc, or if it's 0, we do nothing. And uvm-alloc is passed the old size and the new size. So here we're capturing the old size from the proc structure, P, and adding a positive number to it. And if there is any problem, for example, if the pages cannot be allocated, we return -1. Otherwise, we will be returning 0. If we are shrinking the address space, then n is a negative number, and here the old size is larger than the new size, and uvm-dealloc will always succeed, so we don't need to check. But in any case, both of these return the size of the address space afterwards, so we save that in the size field of the proc structure. Okay, that's it for the anatomy of a system call. I will see you in the next video.